because our uncertainty in what it's doing has to be very big, and our uncertainty in what it's doing can't get big unless it's doing a lot of stuff. Is that clear? You can't mistake this chart by a pound. I'd have to have a whole box. Or you can't mistake it by a ton. I'd have to have a whole truckload. So, in order that our uncertainty in the momentum should be big enough to match the lack of uncertainty in where it is, the momentum would be enough to drive it off. Now, you have to understand this. The only reason, remember we started out that the universe is made out of hydrogen. And as I always say, since the whole universe is made out of hydrogen, if you can understand hydrogen, you can understand anything. Now this is our hydrogen, and it exists like this because we cannot tell what's happening. Is that clear? You cannot tell what's happening. If it sits down there, you could know where it is, then you can't know what it's doing. Or you could know the other way around. You can know what it's doing, but not know where it's doing it. You can know one of the two, but you can't know both of the things. All right. Now what else was I going to say? Oh yes, I was going to say. So this is what do you call a thing which exists because you don't know what it is? A ghost. A ghost. The existence of a ghost depends upon your not knowing what's going on. You look out the back window, you hear a noise in the yard, and you look out the back window, and you don't recognize her, and you think she's a ghost. But as soon as she calls out to you, you know it's Sally. Then the ghost disappears. But until you know it's Sally, you don't know it, and that's why you call it a ghost. And I'll show you how you write ghost nowadays, like this. Like that. Now this H is Planck's constant, and the bar through it means Planck's constant over 2 pi. That's how the physicists write it. You even have it on the computer, H with a bar. They even have it on the computers, because they use it all the time. Now why don't you fall through the floor? Come on, it's the same problem. Why don't you fall through the floor? Why doesn't the cotton candy of your feet sink down into the cotton candy of the floor?
It would take too much energy.
It's a different neutron.
What?
It's a different neutron for energy.
It's because if you squish the electrons too close to the nuclei,
Yeah, it's a different.
you know too much about where they are. If you know too much about where they are, they'll buzz harder and push you up. Isn't it neat? But that's the way the world is made, and I'm not responsible for it. You have to remember that. I'm just a tour guide. Nothing more than a tour guide. So you can practice like this. I'm going to buzz them over here and unbuzz them over there. Now I'm going to buzz them over here and unbuzz them over there. Now I'm going to buzz them over here and unbuzz them over there. You can walk like that, it'll help you. But the problem now is to salt this information away. Now, if you can't handle these 3 statements, you have thrown in your sponge. So if you have any trouble with any of those things, get on my case. I'm here to make it as clear as possible, and you're here to see that I do it. But you have to do your part. You have to see to it that I make it clear to you. If any one of those things is spooky, you get me on my case. Yes, what?
On the separation, I wasn't sure why you subtracted time squared.
Because that's the way the universe is.
Well,
And as I said, I'm not responsible.
yeah.
These are statements about how matter behaves. These are not edicts. It's not that Einstein requires that there should be a minus sign in there. Einstein is describing how the universe goes, how the geometry goes, and this is how it goes. Time is anti-space. And that's why it has a minus sign, not for any other reason. Now the interesting thing is this. We see time against two directions in space, the gravitational direction and the electrical direction. We see gravity against two directions in the electrical field, the plus direction and the minus direction. We see electricity against two directions in the magnetic field, the spin-up direction and the spin-down direction. Don't you see? It's a whole bunch of pairs of opposites. But it's not just gravity which pulls and something anti-gravity that pushes in exactly the same way that gravity pulls. Then you can't get a universe. It would be no force at all. So it doesn't go like that. It goes time against two directions in space. It's gravity against two directions in the electrical field. It's electricity against two directions in the magnetic field. It's one against two, against one against two, against one against two. But it looks to me as though it's a boo-boo. Now, if it's a boo-boo, it has to be pairs of opposites. Otherwise, it would represent a change in the changeless. Don't you see that? If it weren't a pair of if it were made on anything but pairs of opposites, it would represent a change in the changeless. But when you look at the physics very carefully, by gum, it's time against two directions in space, and it's gravity against two directions in the electrical field. Okay, it's one against two, and the whole thing goes to zilch. But the energy doesn't go to zilch. The energy does not go to zero. And now the question is, what is energy?
Is energy what both have in common,
Yes?
which makes it opposite, which makes it like opposite pairs?
I'm not quite following what you're saying. Try again.
Before, the statement was that if these are opposite pairs,
Yes?
they should have also something in common.
Oh, yes.
And if
All right, let's do the common. Space against time, they both live under the same house. They're both in the same equation. So they're a pair of opposites. They're identical, they're both dimensions. Do you have any more trouble with them being opposite, being identical?
I'm not sure yet.
And gravity winds things up to 500 atom miles per pound by winding them together. Electricity winds things 500 atom miles per pound by winding them apart. But they both wind up to 500 atom miles per pound. One in, one out. And plus and minus, you already know they're electrical. You don't have any trouble with them being identical. And north and south, you don't have any trouble there. But what we didn't know before was how come we knew these were opposites, we didn't know they were identical. We knew they were opposite, we didn't know they were identical. But you can't have a pair of opposites without having them identical in some way. That's what's so funny about red, white, or moist. Neither red, white, nor moist. Well, moist doesn't fit with red and white. Now, there was something else I had to tell you, and I've forgotten what it was. What do I have to tell you now?
So the energy is not what is common of both. Yes, it is.
Oh, yes.
The common,
Oh, yes.
Yeah, okay.
Energy. Now, let me ask you a question. When you say that you know where something is, what do you mean by that? When you say that you know where something is, what do you mean?
I mean, I can find it.
You're not
How do you find it?
there.
How do you find it? By looking through the other things with respect to which you know its position. Okay? You know where it is with respect to other things. That's what you mean when you say you know where it is. You know that Kaslo is in British Columbia. It's north of Washington. Are we still north of Washington?
Mm-hmm.
Okay. Or Oregon. Washington, aren't we? Can't, well, we have to go north of Oregon too. But we're not north of Idaho, are we? Washington. All right. So that's what you mean. Now, you also mean another thing. You mean that it's small enough so that you can designate its position. Now how come on a road map they can say how far it is from San Francisco to Los Angeles? Los Angeles is about 60 miles across. How can they put down on a road map how far it is from San Francisco to Los Angeles? They do it from post office to post office. I used to think they did it from City Hall to City Hall, but I'm told they do it from post office to post office. Now, post offices are small with respect to a mile, so they can put down the distance in miles. If they had to do it in feet, they'd have to go from the flagpole to the flagpole. Is that clear? And if they had to do it in millimeters, they'd have to do a scratch on a bolt. Got the picture? Now, when you say that you know where something is, you mean that you know where it is with respect to other things. And with respect to the proton, you mean that you know where it is with respect to all the other matter in the observable universe, and it wound up against gravity to 500 atom bombs per pound. And when you say that you know where it is, it's because it's small enough so that you can say where it is, and that winds it up against electricity to 500 atom bombs per pound. And if you say that you know where it is, you know where it is in space and time, and that winds it up against the uncertainty principle to 500 atom bombs per pound. Now we haven't put that one in. So let me put that one in. I have this story about Auntie Nancy. Auntie Nancy has a basketball court outside of her mother's window. Got a basket over here and a basket over here. And her mother has a window over here. But her mother can only see half the court. She can't see the whole court. So if she insists that Nancy should play at half a court, Nancy will be so violent she'll jump out of the court altogether and go downtown, have her hair done. If her mother is more lenient, she'll play in the whole court and she'll stay there all day. All right. So much for Auntie Nancy. Now we have up here, let me see how to do this. Hydrogen is like that. Oh, if we make the electron sit right on the proton, that would be a neutron, okay? But you know it won't stay. The electron will jump off because you know too much about where it is, so you can't tell what it's doing, and it has enough to do to jump off. Now, suppose instead of having it sit on one of them, we have two protons here, and we have an electron sitting on two protons. Will it jump off? That's a deuteron. Will it jump off? Why not? Because you don't know where it is. It might be over here or it might be over here. You don't know where it is. You know less about where it is, so you can know more about what it's doing, so it doesn't have to do so much to keep you confused. The only reason that the universe is like this is because we're stupid. You might just as well be stupid. There is no other reason behind this. Now, in a helium nucleus, there are three ways to play whole court basketball. Okay? You've got four protons, all touching each other. Each one touches three. I used to have four ping pong balls. You say I put three down, put one on top. Each one touches three. So there are three ways to play whole court basketball. And it is so confusing that the energy falls by 0.7%. 0.7% of the rest energy goes away into some other form when hydrogen goes to helium. Now, if the nuclei could get bigger and bigger indefinitely, then they could get big enough so they have no idea where the particles are. Then the nuclear energy could go to zero. The nuclear energy is also 500 atom bombs per pound. These are two sides and the edge of the same coin. We've got gravitational energy on one side, we've got electrical energy on the other side, and we got nuclear energy, but they're all the same thing, and they're all due to seeing it in space and time. Nothing has happened here, except that we have mistaken something which is not in space and time for something which we see in space and time, and the fact that we see it in space and time automatically winds it up to 500 atom bombs per pound. Now you ask, she's gone. She asked what energy was.
I think she
And
had
now
to
she's
leave at
left.
9.
Energy is the nature of the underlying existence showing through. Energy is the nature of the underlying existence showing through. The infinite shows through in the teeny-weenies and winds them up to 500 atom bombs per pound. The undivided shows through in the divided and it winds it up to 500 atom bombs per pound. And simply seeing it in space and time winds it up against the uncertainty principle to 500 atom bombs per pound. And that's all you see here. That's probably more than enough stuff to dump on you in one night. What time is it?
It's
9:14.
It's what?
9:14.
We didn't start till 14 after, so you can be here for one more minute.
Can you say this in other words also?
In other words,
Yes.
yes, my friends tell me that I should say these things over and over in different words because you can never tell which set of words will catch which person. Now, one of my friends went through my class twice, maybe 3 times, I don't remember. All of a sudden, on the last time, when I put this on the board, her lights went on. All of a sudden, her lights went on. Now, my friends also get on my case for abusing you all. But I told you why I do it. It's just for the fun of it. And I don't want any of you to be upset by it if I jump on you and make fun of you and all those things you say. No, don't be upset by it.
So could you give another picture?
Another picture of what?
For what you said, like the
For the uncertainty
consequence?
principle?
Yes.
La 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 la. What do you do for the uncertainty principle?
Or if we go back to this picture with the 2 protons. and you
This
made-
one?
Yeah, you made a difference to the case to the one.
Yes, because
And I-
here you know where the electron is. It's sitting right on one proton.
Oh no, I don't know.
Well, yes, you do, because the proton is smaller than the electron. When you say that a boy is sitting in a chair, that's one thing. But when you say that he's sitting on a tack, you know exactly where he is.
And the other one, sitting on 2, that's
Yeah.
possible because still he is bigger than 2 of them.
What?
So I can know where it is also.
No, well, I drew it bigger. He's not bigger, but he can sit on this one or he can sit on this one, and you don't know which one he's sitting on. If you don't know where he is.
But
See,
how
the
can you
reason
say
he has to jump is because you know where he is. If the uncertainty in where he is very, very small here. The uncertainty in where he is here is bigger. This is bigger, so this could get smaller.
And this is only because of the difference in size?
It's because here there are 2 places to be, and here there's only 1 place to be.
But if it's 2 places, how could you say that it's 2? That it's 1
Well,
because it
you
sits
see,
on 2?
you might have a house in Kaslo and another house in, say, Atlanta.
That would be wonderful.
And I know. And then you go to Atlanta when it's winter, and you come up here in the summer.
Right.
But you'd have to have 2 phone numbers. We wouldn't know where you are. If you only have a house in Kaslo, we know where you are.
Okay.
But if you have 2 houses, we don't know where you are.
But if you only have a room,
So this
We'll never
is
find
in Atlanta, and this is in Kaslo, and this is you. But we don't know where you are. You're either in Atlanta or you're in Kaslo. But here, you see, if you have only a house in Kaslo, we know where you are.
So what you are saying is that it's only possible to sit on one to one It's
No,
not
no.
possible to be one or two.
Oh, no, you can't, no, the electron is not going to spread around like that, no.
Let them bounce back and forth.
Yes, it can bounce back and forth and keep you confused. You don't know where it is. Now, in a helium nucleus, you get 4 protons for it to sit on, and it can be anywhere. And that's much more confusing. Now, if the atoms could get bigger and bigger indefinitely, which they cannot do, but that's an electrical problem, that's all. That's an electrical problem that keeps them from getting any bigger. Electricity blows them up, not something else. And we have to talk about bombs. Next time, you remind me, we've got to talk about bombs. Can you remind me about bombs? Now, I'll tell you one thing. When I get to gravity bombs, all the kids get out paper and pencil. So we have to talk about bombs next time.
So
Yeah.
in other words, what we're saying basically is the hydrogen bomb is the result of locating where each of those charges were and releasing the energy.
Hydrogen bomb is the energy you get by letting the electron, by letting the hydrogen atoms fall together to helium, so that you don't know where they are anymore. You can play whole court basketball all around the place like this. Then the nuclear energy follows. Well, let's talk about bombs right now. Can you stay another 5 minutes? We'll talk about bombs right now. Get out your paper and pencil. All right, you don't need it. It's really easy. Hydrogen, gravity bombs are easy. They're the easiest kind to make. All right. What kind of energy do you have in a TNT bomb before it blows up?
Potential.
Of course it's potential. Wash your mouth. Chemical. There are several kinds of potential energy, and potential energy is no use telling me there's potential energy. If I ask you for a fish and you give me a lake, that's not satisfactory. I want the fish. Filet. All right. It's electrical energy, or chemical energy, which is electrical energy and magnetic energy. Electrical energy will do. What kind of energy do we have in the uranium bomb before it blows? Nuclear? How many vote for nuclear? Put up your hands. How many vote against it? Put up your hands. Come on. How many people can be pure gold? Look, I want to know what you think. How many think that a uranium bomb has nuclear energy? Please put up your hands. How many think it does not? Please put up your hands. It does not. The uranium nucleus has too much electricity inside. I'll draw you a picture of a uranium nucleus. Here's a uranium nucleus. They're playing whole court basketball here, and whole court basketball here, and whole court basketball here, and whole court basketball here, blah, 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 all over the place, okay? Now it has a skin on it, because this one is playing whole court basketball with something in here and with nothing outside. And this one is pulled inside playing whole court basketball and with nothing outside. So there's a surface tension on it, and it holds it together and squeezes it way harder, billions of times harder than the surface tension under a drop of water. It's a real hard surface tension because they're playing whole court basketball indoors. Now, what you do is to drop a slow neutron into it, just like this. Then the surface tension bites it in two, and the two sides fly violently apart because they have about 45 charges each, 46 charges each. Got it? Got it? It's electrical energy. The two halves fly violently apart because they're electrically charged and they hate each other like poison. The only reason they stay together is because of a tremendous surface tension. And we drop a slow neutron in there and it does like this. It causes it to do like this. And when it's like this, it bites in two. That's electrical energy. What kind of energy do we have in a hydrogen bomb? Nuclear energy. They're going to play whole court basketball. That's a lower energy state. Now, how do we make, suppose we want a real big bomb, what kind of energy do we want to use? What kind of energy do we have in major amounts in this universe? Gravity. So we want to make a gravity bomb. How do you make a gravity bomb? Come on, cheer up. How do you make a gravity bomb? You make it out of old, discarded iron bathtubs. You collect all the old discarded iron bathtubs that you can find, and you throw them in a pile. When the pile gets as big as the sun, stand back. It will sterilize the entire solar system and probably everything out as far as Sirius. If there's any life this side of Sirius, it would probably kill it when your gravity bomb goes off. It would be a supernova explosion. Now you have this problem. You've got to allow time to get away. You know how bombers are. They want to get out of there. So you have this problem. You want to get out. So you have to have a very fast spaceship standing by. And it's going to take you 1,000,000 years to get away anyway. So you have to get a good start. So how do you get this thing to slow down? Before your pile gets quite big enough to go, you throw Jupiter into it, because Jupiter is made out of hydrogen, and it's got to get cooked down to iron before it can go. And throw in Saturn, and go to some other solar system and get a few other things like that and throw them into hydrogen things, so they have to cook down. And allow yourself about, maybe 500 years, and at least 500 years head start to get away. And then you have to be in a real lickety-split spaceship, or you're going to get singed anyway, and you will anyway. There's no way to get away from it. Anyway, that's a gravity bomb. They go off every now and then. I've seen 3 or 4 of them. I saw one in Andromeda, I saw one in M83, I saw one in M101, and I saw one in the Large Magellanic Clouds. How many is that? 4 or 5? 4. Oh, I see one in M101. That's 5. I've seen 5 of them.
You said 101.
No, but I saw one in M81 too. I saw one in 101, one in M31, one in M... Did I say 81? 101?
31, 81.
83, and the Large Magellanic Cloud. There's 5. So cheer up. You can see them every now and then. Now, I told you about Tycho. Tycho was away on his honeymoon, and he saw a supernova, and he canceled the honeymoon and went back to his observatory. My hero. Well, now I think you should scram. Now I think you should scram. No, not till I give you some homework. Just stick around. The homework for this time was supposed to be in addition to what is space and what is time, or what's the relationship between them. We went through that. You were also supposed to have, why won't the electron sit down in the proton? But we got by that already. We got by some of the consequences. So now I'll have to give you some other problems. Now the problem is going to be, we're going to have to talk about all this some more, but there's also going to be this problem. If this is a boo-boo, why do you go on with it? Why do you go on with it? So now we have to know what happened to us that didn't happen to the chimpanzees. And what happened to the women that didn't happen to us jerks. You know, it's really like that. Women were invented by men, and men were invented by women, but we did a better job. Now I can get it.
Do you want to do it again tomorrow here?
What?
Again tomorrow here?
Of course, again tomorrow here.
7 to 9?
We just started. As soon as you understand everything, don't come back anymore.
And I didn't understand the homework up to now.
Well, the homework for tomorrow is what happened to us that didn't happen to the chimpanzees? Because the chimpanzees never come to these things.
I don't know.
Chimpanzees are some of the great apes. There's several kinds of great apes. There are chimpanzees, there are orangutans, there are gorillas, and there are us. There are 4 of us. That's all the great apes there are. 4 of us, and the body language of all 4 of us is the same. I was at the San Francisco Zoo and I had an orange in my hand and the orang said, just like I said to him. There's no way to misunderstand it for any grade 8. Dogs might not understand it because they don't do like that. They don't have hands to do it with. But all the grade 8s have hands. And all the rest of them have hands down here. We have feet down here, but the rest of them have hands down here. Something happened to us that didn't happen to them. And they've got anal callosities back here. They got shoe soles back here because they sit in the branches of the trees. You got a beach bum. If you want to know what your ancestors were up to, take off all your clothes and stand in front of a full-length mirror. It's written all over you. The only animals who have shoulder blades parallel this way are animals that swang in the trees. I know it's not proper English, but I like it that way. Animals that swang in the trees. And your shoulder blades are parallel this way. All the rest of them have them parallel this way. You cannot crucify a donkey. You cannot crucify a donkey. By the time you got him nailed this way, he'd be split right up. One half. Never mind. So what our ancestors did is written on us. But we have a lot of differences from the other great apes, and you'll have to see if you can explain them. What happened to us that didn't happen to the chimps? Because genetically, our DNA is less than 1% off of theirs. Less than 1% off of theirs. By the way, do we have a video machine that we can show here?
Yes,
I
we
think
do.
it's very.
I have a half-hour tape.
Well, we can work it out one way or another.
Okay, we can bring mine.
If you can get a TV screen and a VCR, I've got a tape.
Okay, you want
Just
to?
like I always say, you get the people in the ears, I've got the yakety yak.
Okay, we'll do it. We'll find it somewhere. I know I've got one in the back, but it may be buried. We may have to.
Anyway, you've done a fabulous job to get so many people here. You really have. This is not a very big town to have this many people.
We have some
I
really
can
good
hardly get
people
this
here.
many people in a big city. Well, I didn't try it in Sao Paulo. Well, I thought Sao Paulo was a fairly small town, but when I got there, I found that the population of Sao Paulo was 25 times the population of San Francisco. Those great, big, tall apartment houses go as far as you can see out of sight.
Oh my gosh.
Time is grand.
So it's 7 o'clock tomorrow.
Now, there's one reason why the academic field has gone like this. Because you get a proton and an antiproton, or an electron and an anti-electron, and they disappear into radiation. All of a sudden, we have energy without mass. Must be E plus M equals K.
Oh, wrong tape.
But you see, in order to see it that way, you have to overlook special relativity. That no such thing happened. When the energy is picked up, between those, they're going to have a test right now.
We're supposed to get books first. Words is books first, test second.
No, books later. I'll get those out here. Relative explosion. There it is. There it is. You have to see this picture. Can you see the picture okay?
Would you put it over here too so I can get a picture of it?
All right, when I get over there, you'll get it. You kids are going to get a big charge out of this.
Okay. Where is it? Oh, I'm too close. Okay, that's great. Okay, thank you.
Now I'm going to read to you. These are the first paragraphs of a book called The Relativity Explosion by Martin Gardner, who used to write, I don't know if it is or not, Mathematical Games for Scientific American. Two sailors, Joe and Mo, were cast away on a deserted island. Several years went by. One day Joe found a bottle that had washed ashore. It was one of those new king-size bottles of Coca-Cola. Joe turned pale. "Hey, Mo," he shouted, "we've shrunk." There is a serious lesson to be learned from this joke. The lesson is there is no way of judging the size of an object except by comparing it to the size of something else. The Lilliputians thought Gulliver a giant. The Brobdingnagians thought Gulliver tiny. Is a billiard ball large or small? Well, it is extremely large relative to an atom, but extremely small relative to the Earth. Poincaré, a famous 19th century French mathematician who anticipated many aspects of relativity theory, once put it in this way. Scientists call his way of putting it a thought experiment, an experiment that can be imagined but not actually performed. Suppose, he said, that during the night, while you were sound asleep, everything in the universe became 1,000 times larger than before. By everything, Poincaré meant everything. Electrons, atoms, wavelengths of light, you yourself, your bed, your house, the earth, the sun, the stars. When you awoke, would you be able to tell anything had changed? Is there any experiment you could perform that would prove you had altered in size? I'll give you a moment to think about it before I get a show of hands. How many think you could tell in the morning? How many think you could not tell in the morning? Please put up your hands. I want you to all vote one way or the other. None of this lazy stuff. You vote one side or the other. I want to know what you think. How many think that you could tell in the morning? Please put up your hand. How many think you could not tell in the morning? Please put up your hand. All right. I could easily tell. You see, what Poincaré does not know is that if things become bigger in the gravitational field, they become more massive. And if they become bigger in the electrical field, they become less massive. And how could you do both? The only way you could do both is to change the ratio of the gravitational field to the electrical field. So let me ask you this question. There are two all-American forces, gravity and electricity. Gravity sucks and electricity pushes. And between two protons, electricity pushes and gravity pulls. And they both operate in the inverse square law. Is that clear? So that whatever the ratio of the forces is, it's the same at all distances. If you go twice as far away, they fall off to a quarter. They both fall off the same way. All right. So how much stronger, if it is stronger, do you think the electrical push is between two protons compared to the gravitational pull? What?
None?
Oh no, it's a lot stronger.
It's just for what?
The electrical push is a lot stronger. Shall I write the number on the board? All right. Hang on. Gotta make myself some space to do the writing. Not such a little number. This many times.
Infinity?
That many times stronger. But it's a real number. It's the same at all distances. Now let me ask you this. The universe is made out of hydrogen. Falling together, these hydrogen clouds fall together by gravity. Let me ask you, if one electron, well let me tell you something first. If one electron in a billion billion, that's a billion to the fourth power, that's a billion 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 billion. That's how big that number is. A billion billion multiplied by a billion billion. If one electron in this hydrogen, one electron in a billion billion hydrogen atoms, only one electron in a billion billion hydrogen atoms, had too much electrical charge by only one part in a billion billion, the electrical push would keep the clouds from falling together. Now what would happen if one electron in a billion billion had too little electrical charge by one part in a billion billion? Then what would happen?
They'd fall together.
You think they'd fall together? You get to vote on this. How many agree with him they'd fall together? Put up your hand. How many think they would not fall together? Please put up your hand. Of course they would not fall together. You have too much charge on the protons, you silly geese. It doesn't make a particle of difference whether it's too much or too little. You cannot get things to fall together by electricity. Electricity is anti-gravity. It does nothing but push them apart. There is no way to fiddle with it so that it brings them together. Now, what do I need to quiz you on? All right, I've got another quiz for you. Suppose we were able to take all the rest of the universe away, I mean make it disappear so that it doesn't exist at all. Would we be able to tell that the Earth is going around the sun?
No.
You get to vote on this. How many think we would still be able to know that the Earth is going around the sun? Please put up your hands. How would we know?
Still have
What?
seasons.
I don't know. We'll stop the spin of the Earth.
Okay. That there's been right today.
But that's the spin of the Earth. That's not because we go around the sun. We go around the sun once a year, not every noon.
But there would be a light part of the year and the dark part.
Yeah.
So you would know you'd be going around it.
Yes, but we just stopped the spin of the Earth.
Yeah, that's why.
So then one side's going to be bright, one side's going to be dark. We'll allow that. That would be all right. Can we tell that we're going around the sun once a year? Once again, how many think we could? Please put up your hand. Uh-oh. Hands are getting scared. How many think you couldn't? Please put up your hand. Well, if it wasn't going around, wouldn't it fall in? No, you don't know that it would fall in. Because the only reason the sun and the earth have that amount of mass is because they've been separated from all the rest of the matter of the observable universe. And if there wasn't any rest of the matter of the observable universe, we have no idea what the rest mass of the sun would be or the rest mass of the earth. And we have no idea whether we could tell. See, at first you think, well, you wouldn't be able to see the black stars going
That
around.
was a trick question.
No, it's not. It's a straightforward question, and you should have shaped up. It's not a quick trick question. It's a tricky universe, if you like, but it's not a trick question. First, you assume that if there's nothing to compare it with, you wouldn't notice. But then you wake up a little bit and you notice, but it would have fallen in. But then, only at the end, when you're real smart, when you get through this class, then you're smart enough to know if the rest of the universe wasn't there, you don't know whether the sun would pull on the earth or not. Okay. What else can I quiz you on? I haven't quizzed you enough. Yeah.
Can we go back to the question about the electron having less charge, just a little bit less charge?
Yeah.
Wouldn't the gravity that exists pull it faster because the charge is less at that
No,
point?
because then the protons have too much charge. The electron charge is the exact opposite of the proton charge. And since we have the same number of both of them, the total charge of the universe is zero. And if it were not zero, to 36 places, gravity would not show. And it doesn't matter which way it's out of balance. If there's too much negative charge, it keeps them apart. Or if there's too much positive charge, it keeps them apart. It don't make no, never mind which way it goes. Is that clear now? It don't make no never mind which way it goes. What else can I quiz them on? I haven't quizzed you anywhere near enough. You see, you have to work your heads, you see. When you work your heads, you know, in school, they give you all these problems to work at the end of the end of something or other. And that's so that you get some practice using your own brain. Let me think of some other quiz that I can ask you. Well, I asked you, why don't you fall through the floor? Have you all got that straight now? Have you all got it straight why you don't fall through the floor?
By experience.
You're not supposed to shake your head this way. It's supposed to go this way. Because if you were to, well, you can think of the floor as like cotton candy, and your feet as like cotton candy, because the nuclei of the atoms were the size of garden peas. The electron clouds around them would fill football stadiums. I know you don't happen to have one at Kaslo, but you know what they look like. That big. So this is mostly like cotton candy. It's mostly just fuzzy stuff, see? You remember, in a neutron star, it collapses to 100,000 battleships in a one-pint jar, okay? This is a good vacuum. So the question is, why can't the good vacuum of your feet sink down into the good vacuum of the floor? And the reason is, because if you tried to do that, you'd push the electrons too close, to the nuclei of the atoms. And then Heisenberg says you can't do that, because if you knew that they were that close, you can't know what they're doing, and they'd have to do more. If you push them in closer so you know more about where they are, you have to know less about what they're doing, and in order to keep you so stupid, they'll do more. I know, you people don't think that the whole thing is related to you, but it is. There's no such thing anymore as a description of a universe, except with the author of the description. It's as seen by Heisenberg, or as seen by Einstein, or as seen by you. And I'll give you an example just in a moment. Yes, what?
Well, I just have trouble with this whole thing that you seem to sort of attribute some sort of consciousness almost to these electrons, that they have to keep us confused, and if we know too much, they'll do something else to keep us confused, but it doesn't really explain why they're acting the way they are.
But I explained to you last night why it's like this. It's because the whole thing is a boo-boo. Right?
Well,
The whole thing is a boo-boo. If you see things the way we see them, now's the time to ask you a question, you see, about the gunas. Yeah. In India, a long time ago, they had this notion that this is a boo-boo. It's a very old notion. They had it a long time ago. And they had some very interesting statements to make about it. They said, if you make a boo-boo like this, like mistaking a rope for a snake, or mistaking to change the infinite the undivided for this stupid universe which we see, there are three things you have to do. You have to fail to see it rightly. That's called the veiling power of Thomas. You have to jump to the wrong conclusion. That's the projecting power of Rajas. You jumped to the wrong conclusion. Nobody forced you to it. But you had to see it in the first place. That's the revealing power of Sattva. They always leave it out of the books. They leave it out of the books. Jerks. These three things make up this boo-boo. Failing to see the rope rightly allows you to jump to the wrong conclusion that it was a snake. But if you hadn't seen the rope, you might have mistaken it for a submarine. It's the length of the rope that you saw as the length of the snake. So you have the veiling power of Thomas, you do it in the dusk, the projecting power of Rajas, because you're so anxious to see something, and the revealing power of Sattva, you had to see it in the first place, or the mistake would have gone some other way. How did I get up to all that? So, you see, if this is a boo-boo, there's always a boo-booer. Let me give you another review. We have these 5 senses of perception. Now, the ancients, you know, they had these 5 elements. Gravity with the ears. Are you all aware about that you know what's down with your ears? Are you all aware of this? Probably you're not all aware of this. You've got three things that go on in your ears. You've got the saccule. You've got a little sac of hair cells in there with a little calcium carbonate crystal in there. And when you tip your head this way, it rolls that way and tells you your head's tipped to the right. Well, you're tipped to the left. Okay? Now, I was raised by a zoologist, you see. Now, crabs, when they molt, they have sand grains in there. They have them open to the outside. They don't have little calcium carbonate crystals like we do, because ours are all closed up inside. You can't get to them from the outside. But crabs, you can get to them from the outside. So when they molt, they have to put sand grains in there. They have the proper equipment. They put sand grains in there. Now, when they molt, if you give them iron filings, they'll put them in there. Then you put a magnet over there. They'll fill themselves violently over that. There's some advantages to being raised by a zoologist, you see. All right, so gravity we have in our ears. This is what the ancients said. The first of the five elements is you have it with your ears. The second one's with your skin. That's temperature. Temperature is a measure of the mean kinetic energy of the molecules. Radiation with the eyes. Nobody has any problem with that. Electricity with the tongue. Do you all know what that means? See, chemists know certain things that not everybody knows. Do you know what tastes sour? Protons taste sour. Nothing else in the universe tastes sour except protons. And it just happens that the whole universe is made out of protons and electrons. And if you take the electrons away, the whole thing is sour.
Does that mean ants are more protons than electrons?
They have formic acid. Now you see, the physicists call them protons. The chemists call them hydrogen ions. You must have noticed. They discuss it on Sundays if they talk at all. I think they talk at leap years. Anyway, so we have these five senses of perception.
You missed the fifth one.
That's magnetism with the nose, because the molecules which we smell with our noses are held together with electron pair bonds, and those are magnetic bonds. So that's all magnetism that we get with our noses. So we see these five different kinds of energy with our five senses: gravity, kinetic energy, radiation, electricity, and magnetism, because, and only because, the individual protoplasmic cells respond to the same five kinds of energy. See, we think we're so smart. But you see, the reason the protoplasmic cells respond to these five kinds of energy is because the atoms do. The atoms also read gravity, kinetic energy, radiation, electricity, and magnetism. So don't think you're so smart. Now we had this big conference in Michigan years ago. These big physicists got on my case. And the title of my talk was Matter as Sentiency. And they made me talk first, so all the physicists could jump on me, which immediately they did. Oh, they were nasty, furious and nasty. So at the end, you see, there came this question, and I don't remember the question anymore, but the question landed on me. And I said, I know you think of yourselves as very sophisticated beings. You know where down is. But if you really want to know where down is, you hang an insentient piece of lead on an insentient piece of string. And nobody opened his mouth. The lead knows where the earth is, and it knows damn sight better than you do. That's why you do it that way. You could just guess to get the doors right side up. And then when you come in the morning, you thought you blew it. But you see, the lead knows how to do it right. All right, now how did we get into all of that? We were going to talk about stars. Are we ready to talk about stars? Did you get your Buddha straight? And your five elements straight? You see, somehow or other, a long time ago, there were some real smart physicists, because we didn't get the chemical elements figured out in Europe till about 200 years ago. I don't remember Mendeleev's dates, but it's about 200 years ago that we got the atomic table straightened out. But the energies of this universe, we didn't have straightened out like they had a long time ago in India. They had them a long, long time ago, and they had them in the right order. Gravity makes things fall, then you got kinetic energy. Electricity makes things move, and then you got magnetic energy. And in between, you got radiation. And they had this all figured out like that a long time ago. Anyway, so those are the five, what they call gross elements. There are 5 subtle elements, and we don't want to talk about them now. We're nowhere near educated enough to talk about those things, but maybe we will before we get out of here. Now we need to talk about stars.
Before we talk about stars, in fact, my question, I find it interesting what you say about the 3 gunas, even reasoning of the mind. But what I was trying to find the correspondence because Thomas has thought it had to do with gravity.
No!
It doesn't. Well,
Now you know why I yell at you like this.
no,
So
no.
that people will know that that's terribly wrong.
Okay, but tell me with words, not just with sound.
The gunas are the way I told you.
Yeah, yeah, no, I
Thomas
understand
is
that.
the
but
veiling
that's it,
power.
right.
You're failing to see it rightly. Rogers
But
is
also this thing, for instance, if you eat onions, you get thermasic because onions are roots in the
This is
ground.
bullshit.
That's bullshit.
You see, some notion floats across the continent, and you have 300 million people to mistake it.
Oh.
And at least 200 million are willing to. At least 200 million are willing to get it wrong. Now, I've heard all kinds of things associated with the gunas, like Tamas is matter, Rajas is energy, and Sattva is consciousness. This is all bullshit. Tamas is the veiling power.
Yeah.
If you make a mistake, you had to make a mistake to make the mistake, that's the veiling power. But you had to jump to a wrong conclusion, that's the projecting power. And you had to see it in the first place, that's the revealing power. Now, there's another bunch of people in India called the Samkhyans, and they don't believe that the first cause of this universe is a boo-boo. They think it really happened. They think it's really a happening, okay? So they don't know anything about the right use of Tamas, Rajas, and Sattva. They don't have it in there at all. So they have to think of them as chemicals. Take a certain amount of Tamas and a certain amount of Rajas, and you make a cat. Change the proportion, you got a dog. Put in more Tamas, you got a stone. It's bullshit. It has nothing to do with the Tamas, with the guna idea at all. So those are the Sankhyas. They never could figure out what the gunas were for. And so they thought that Rajas is energy, activity. You look in the Sanskrit dictionary, there is no mention of activity related to Rajas. It's mistaking something for something else. Look in the dictionary, they can find some kind of thing. Oh yes, I was going to tell you something else. There has to be an observer in this thing. You see, all these little particles are like tops. They're spin up and spin down. Why do we call it spin up and spin down? Do you all understand what I mean? All these little electrons and all these little protons and all these little things are spinning. And they're spin up and spin down. The reason we call it spin up and spin down is because when we look at them, we have to see them with a magnetic field. And when we put a magnetic field this way, half of them are spin up and half of them are spin down on that field. Nobody is spinning kiriwakas. They're spinning on the field. Then we change our field this way. They're 50% 15, they're 50% spin up and spin down on that field. Put it this way, don't make no, never mind which way you put your field, they're 50% spin up and spin down on your field. Now the question is, what way are they spinning when we're not looking? Now the question is, what is the snake doing when we're not mistaking the rope for it? There is no talk of what the snake is doing when we're not making that mistake. Now the physicists you see at the university, they've come to the conclusion there's no such thing as which way they're spinning when we're not looking. You might think they're spinning every which way. No, we can prove that they never spin every which way. All right, now we can talk about stars, now that you're back in here. We can talk about stars. We mentioned, oh, did you tell me why you don't fall through the floor? Yeah, I just told you why you don't fall through the floor. Because if you tried to fall through the floor, the cotton candy of your feet would squish down into the cotton candy of the floor and push all the electrons too close to the nuclei, and then they would spin harder and keep you up. I told you wasn't it last night or you can do it like this. You're going to buzz them over here and unbuzz them over there. I'm going to buzz them over here and unbuzz them over there. I'm going to buzz them over here and unbuzz them over there. If you walk around like this, you'll understand it better. You see, it's not clear to us why we don't fall through the floor. It really is not clear to us at all that when you pound two hammers together, face to face, they don't touch each other. You just squish the electrons too close to the nuclei and the hammer responds away. You probably thought the hammers hit. No.
Probably also
What
hurt
sound
them.
is it?
What?
Probably also hurt them.
Yes, you can hear it too, but that don't make no never mind. That's just an air problem. All right.
If you pound on your finger,
What?
if you pound with a hammer on your finger,
I know. That's called hitting the nail on the thumb.
well, you're gonna, that.
That's better than hitting the nail on the
Is it
head.
pushing the other way? Not hard enough, eh?
Anyway, no, you don't hit your finger. All right. Now the next question is, how come in a black dwarf star we have squeezed it down to 100,000 pounds in a 1-pint jar? What has happened to Heisenberg's uncertainty principle?
Well, if you know you must know pretty well where they are, because they're so much enclosed in a small space, or you really don't know what they're doing at all.
That's right. And they buzz off. You must have heard it. Buzz off. They have buzzed off the atoms completely. The electrons have simply buzzed off, and the star, if you want, is a jello of atomic nuclei through which the electrons are buzzing in pairs like bats that will never get out of hell. Got the picture? Now the question is, how come you can't squish it any smaller? That's because if you did, you have too many electrons in too small amounts. And that's also forbidden. You know too much about where the electrons are with respect to other electrons. That's also forbidden. That's what keeps it from going any further, and it ends up at 100,000 pounds in a 1-pint jar. All right, now what do we do in a neutron star? We squeeze it down to a density of 100,000 battleships in a 1-pint jar. Now what have we done? Don't just sit there. You all have mouths. What?
You blow the electrons off.
No, not so.
The electrons are going in groups of 3 or 4 instead of in groups of 2.
No, the electrons are sitting on the protons. Isn't that forbidden?
You said it was.
No, it's not forbidden. It depends upon how hard they're buzzing. Now this is like a little kid who doesn't want to sit on the john, and you're squeezing him down on the john. And the harder you squeeze, the harder he wiggles. So they're sitting right on the john, but they're wiggling like hell, okay? That's what happens in a neutron star. The momentum is still in there. It's just that gravity's got them squeezed down tight. That's at 100,000 battleships in a 1-pint jar. Now, suppose we had a magic ladle and we reach into a neutron star and take a ladle full of neutrons and throw it out between the stars. When the electrons jump off, you get to vote. If we had a magic ladle and we get a ladle full of neutrons and throw them out between the stars, will the electrons jump off? You get to vote. This is a yes or no. How many think they will? Put up your hands. How many think they will not? Put up your hands. They will. They will. Now, those who said they won't, you can just shut up now. Those who said that they will jump off have to answer this question: whether they'll jump off right away or whether they'll jump off in their own sweet time. Think it over for a moment. You get to vote again. Whether they jump off right away as soon as they get out, or whether they jump off in their own sweet time. Okay, how many think they'll jump off right away? Please put up your hands. How many think they'll jump off in their own sweet time? Thank you. They'll jump off in their own sweet time. This is three statements. This is what we cannot know about where they are in the x direction against the momentum in the x direction, and what we cannot know about where they are in the y direction against the momentum in the y direction, and what we cannot know about where they are in the z direction against the momentum in the z direction. But there are only three directions, right?
What about time?
North, west, and up and down. Okay? So there are only three ways to do it in space. So this is three statements, but how many dimensions do we have in this world?
4.
So what's the other one?
Time.
So we have to put the other statement in here. What we cannot know about when something happens, multiplied by what we cannot know about the time component of the momentum. What is the time component of the momentum? The energy can never be less than our little friend that we don't have to know anything about. If you know when it has some energy, you cannot know how much it has. If you know it has enough energy to jump, you cannot know when it has it. They'll jump off in their own sweet time. And in particular, half of them will have jumped in about 12 minutes. If you wait for another 12 minutes, will the rest of them jump? Half of the rest of them will jump. And if after 1,000,000 years there's one still on there, what's the chance of its jumping in the next 12 minutes? 50-50.
Why 12 minutes, not 13
What?
minutes? Why 12 minutes?
Well, that's the half-life of a neutron in free space. And I'm not responsible. Okay. Now you need to ask me some questions about all that stuff that we went through yesterday. We went through way too much stuff last night, and you've got to get on my case and make me say it straight. Unless you all salted it away already, which is dubious.
I'm still having problems with this not being able to know things. You use the example of a car traveling down the street with timed lights.
Yeah.
And if
Then
you
if
knew
a
where
car-
it was, you could know speed.
Right, if a car goes through one light, you can tell where it is all right, but you have no idea what its speed is, because you can go through one light on the street where they're set for 30 miles an hour. You can go through one light at any speed. Two lights at almost any speed. But by the time you get up to 10 lights, it's a little bit restricted. By the time you get up to 100 lights in a row, it's very much restricted. But 100 lights is a big speed, and you don't know where the cars are. Now, in the Stanford Linear Accelerator, they make the magnets go just right so that you know how fast the things are going. You have no idea where they are.
But with a car, you
You
can
just open all the gates like
know.
that.
And with a car, you can know how fast
That's
it's
I
going
know,
and
because you're going to be
exactly
driving
where
the car. This was just an illustration. You have to push it all over the ring, you see. When it comes to electrons and protons and things like that, there is this severe difficulty. Every time you do an experiment to find out where they are, you have to spoil what they're doing. And every time you do an experiment to find out what they're doing, you have to spoil where they're doing it.
Right, that's the effect of the experiment on its natural state. But that doesn't mean you can't, that doesn't mean that theoretically
Yes,
you
it
can't.
means that theoretically you can't.
I don't see that connection. Just because our experiments tend to interfere with what's going on, so we can't.
Yes, but you can't
See.
find out anything any other way.
Right, so we can't know, but that
See,
doesn't-
you might think that we can see all these things with all this light shining on us. That's fine. So you don't have to shine your special flashlight. I don't have to shine a special light on you. So we don't notice that these lights disturb everything. But you see, if you want to know where the electron is, if you want to know where the electron is in here, and you shine a light on it, it will go kitty-wampus out of there. So what are you going to do to find out where it is? How are you going to get the information on where it is and what it's doing? You're going to have to get some information from it. And if you shine a light on it, it's all over. So what will you do? So you'll shine something that doesn't disturb it so much. You'll shine radio waves on it. Okay? Radio waves won't knock your kitty-wumpus out of there. But they have a wavelength this long. And you're trying to find out where the electron is next to the proton. And your measuring stick is this long. It's like trying to find out how long a beetle is by driving along and reading it on your odometer. You follow me?
Yeah.
Anything that you do that allows you to get the information without disturbing it won't carry enough information for you. And anything that you do that carries a lot of information knocks the kitty-wumpus out of there. Now, when it comes to a choo-choo train, you know, you can shine your light on and it doesn't do anything very much to the choo-choo train. But then you can't know where it is to this tolerance either. The only reason you can, remember I asked you last night, what do you mean when you say that you know where something is? You mean two things. You mean that you know where it is with respect to other things. And you mean that you know where it is because it's small enough so that its position could be designated. Now you see, if I ask you where Los Angeles is, it's 60 miles across, and you can't tell me where the hell Los Angeles is. So the people who make road maps, they go from post office to post office. Since the post offices are small with respect to a mile, they can designate it. If they had to do it to a foot, they couldn't do it to a post office. They'd have to do it to some place on the post office. Say the cornerstone or the flagpole. That's the problem. And here we're talking about where the thing is in an atom, you see. Then the problem is severe to find out where it is and what it's doing. And it turns out to be totally impossible. It's impossible for camels, it's impossible for choo-choo trains, it's impossible for electrons, it's impossible for anything. Now I think I told you last night, didn't I? That Richard Feynman said one time, that the paper said at one time that there were 12 people only on Earth that understood relativity theory. He says, I don't believe there ever was such a time. There was a time when only one guy understood it, because he's the guy that figured it out and hadn't written his paper. But he said, once Einstein wrote his paper, quite a number of people understood relativity in some way or other. But he says, I think I can safely say that no one understands quantum mechanics. Now, Richard Feynman says that all of quantum mechanics is right here on the board. There's nothing else in quantum mechanics that's not here on the board. It's a 6-year course at Caltech. But it's all right here on the board. Every statement in quantum mechanics, he says, is a restatement of Heisenberg's uncertainty principle. But there's a reason why we have the uncertainty principle. Because when we look at things, we get mixed up in what we see. Now you see, if it's a boo-boo, there's always an observer mixed up in this boo-boo. The rope does not by itself become a snake. It doesn't go that way. You have to be there to boo-boo it. And the way you boo-boo it depends always on you. There's always a boo-booer. Any more problems? As I said, I'm here to make this as clear as possible, and you're here to see that I do. Don't let me get by with something. Yeah?
You speak of light disturbing the electron.
Yeah.
Light energy?
Yeah.
You touched briefly on photons.
Photons? What about photons? Not photons.
Photons. I was always curious, they say that a photon traveling at the speed of light has zero mass.
There is no such thing as a photon, and there's no such thing as traveling at the speed of light, and the speed of light is not a speed at all. The speed of light is simply the ratio of space to time. Now I'll give you an example. I think I did this before. Suppose we have a spaceship that blasts off at 99% of the speed of light. We're on the station platform. We watch it blast off. The spaceship shoots a rocket out in front of it at 99% of the speed of light. That's not forbidden. The rocket in front of it shoots a bullet out in front of it at 99% of the speed of light, and the bullet has a headlight. The bullet goes with respect to the bullet. The headlight goes with respect to the bullet at the speed of light. With respect to the rocket at the speed of light, with respect to the spaceship at the speed of light, with respect to us at the speed of light, with respect to everything at the speed of light. So what the heck is meant by the speed of light? It's not a speed of anything at all. It's a ratio of space to time. 1 light year is equal to 1 year, or a centimeter is equal to a jiffy. Light goes 7.5 times around the Earth in 1 second. It goes this far in a jiffy.
But if you take an object, take a spaceship and send it at the speed of light through space. And
You can't send it at the speed of light through space.
Okay, but something that's traveling comparable to the speed of light.
All right.
And an astronaut on it has a wristwatch, and an individual and that wristwatch was synchronized to a wristwatch on the Earth, and that individual traveled for, I don't know, X period of time. And you compare the two wristwatches together after that individual stopped, that his wristwatch would show a different time than a person on the Earth.
I am not an expert in this, in the twin paradox, okay? I'm not an expert in the twin paradox. But while he's going away, we see his clocks going slowly, and he sees our clocks going slowly, and that's the same for both of us. So long as he's going away, we see his clocks going slowly, and he sees our clocks going slowly. As soon as he comes back again, we see his clocks going too fast, and he sees ours going too fast. Now, where the twin paradox fits in here, I think, is because it takes too long to go away compared to how long it takes to come back, or something like that. I don't know the twin paradox. I can't handle that.
I think they've done some tests, and although the individual wasn't traveling at the speed of light, but they have compared the two, and they have found that there was a slight difference.
We know that the clocks run differently at the top of a tower than they do on the ground. We already know all this stuff. We already know that gravity does this, and we know that speed does that. That's beside the point, you see. There's no such thing as what speed the clocks are actually going at. There is no actual universe. There just isn't an actual universe. Actual would mean that it arose by a process in physics. Actual means it arises by action. That means by a process in physics. The universe is made out of energy, and it is perfectly well known that energy does not arise by any process in physics. There is no possible way that the universe could be actual. And if it's not actual, you don't have a lot of choices. And one of them is that it's a boo-boo.
If you change the temperature of matter to less than 273 degrees minus Kelvin or something.
You can freeze everything but helium.
But if you drop below 200,
If you what?
minus 273 degrees Kelvin, the matter disappears.
No, it does not. Anything of the sort disappear.
Yes.
Who told you that?
Professor.
Well, tell him to stuff it.
Well, if you could, you can't do it, but if you could.
No, we can get down to that. And everything freezes except helium. Helium has enough wiggle in there. They all have to wiggle, even at 0 degrees absolute. They still have to wiggle. Otherwise, you know where they are, and you know that they're not doing anything, and you can't know that. And even if you get it all the way down to absolute 0, they will not stand still. They'll wiggle. And that amount of wiggle is enough to keep helium from freezing. Only helium will not freeze. Everything else will be frozen. Only helium has enough wiggle to keep it melted.
I was told that if you could theoretically reduce something to that temperature, that it would be non-existent.
Ay, 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 ay. Where did you go to school? This side of the border? I know, that's cruel. But it's not like that. Believe me, it's not like that.
Okay.
And now let me tell you another thing. There was a time when my kid was interested, very much hung up on magic. And I told him, if you think that the magician can make things out of nothing, find out if he goes to the grocery store. And if you think he can make things disappear, find out if he pays a garbage bill. It's easy enough to find out. All right, now what do we have to do?
Can I ask you something?
Yeah.
You said, okay, in conclusion, the universe is a boo-boo. You mean that it's a misperception?
Yeah.
We are creating that idea of the universe.
I don't like the creating the idea of the universe, no, but it's a misperception. We're not seeing it rightly. But there are consequences to not seeing it rightly. That is the interesting thing, because the consequences are right away what we see. If the consequences were something else, I'd throw in my sponge right away. But I'm not accustomed to throwing in sponges, and because the thing comes out just the way we see it. If you don't see, well, first you have to ask, what could exist in the absence of space and time? You don't have a lot of choices. What could exist in the absence of space and time? In the absence of time, it has to be changeless. There's no other way about it. You cannot have change except in time. So if you don't have time, it has to be changeless. If you don't have space, it can't be divided. All dividedness is in space. All smallness is in space. So it has to be infinite and undivided and changeless. Then the problem is, if what exists behind what we see is infinite, changeless, and undivided, how come we see it as changing, finite, and divided? You cannot change the changeless into the changing. You can't do that. You can't cut up the undivided. Okay? So it has to be a boo-boo, that we mistook the changes for the changing. But the changeless has to show. You remember, if you've mistaken a rope for a snake, you had to see the rope. There's no way to make that mistake without seeing the rope. And there's no way to make this mistake without seeing the changeless and the changing. That's inertia. And it's our desire for peace and security. Everything in the universe runs after it. It's not just matter. We also run after peace and security. There's a department of the government. Well, at least on the other side of the border there is. I don't know what you guys do over here. Anyway, but they don't pay me anything. Anyway, and if you mistake the infinite for the finite, the infinite shows in the itsy-bitsy particles. And that's why the itsy-bitsy particles are all electrical. There is no other reason. And if you mistake the undivided for the divided and you think you see it all spaced out, it'll all fall back together like a stretched rubber band. And there's no other explanation for that. Oh, now I get to read to you. She let me turn over the pages in her book, so now I can find them. All right, I'm going to read to you most of a page. I think I read it to you yesterday. I'll read it to you again. Before 1920, our world picture was something like this. The stage on which the universe goes is a three-dimensional space of geometry, as described by Euclid. And things change in a medium called time. Remember, that's our theater and our date. The elements on the stage are particles. For example, the atoms, which have some properties. First, the property of inertia. Now, I don't think of inertia as a property at all. I don't like this property language at all. But that's what he's using. First, the property of inertia. If a particle is moving, it keeps on moving in the same direction unless forces act upon it. The second element, then, is forces. Now, you see, the interesting thing is inertia is a property according to this. And the forces are gravity that make it fall. And electricity that make it fly. Don't you see how funny it is? These three things he's already put in here. The property of inertia, it fights all the changes, but gravity wants it to change, and electricity wants it to change the other way. All of a sudden, he puts all this in. He puts in our stage, and he puts in our date, and then he puts in what's in it. And then at the bottom, he says the other force, that was the smooth one, the long-range force, was called gravitation. This law was known and was very simple. Then in italics he says, why things remain in motion when they are moving, or why there is a law of gravitation, was of course not known. Now nobody at the universities knows why things fall, nobody knows why bicycles coast, and nobody knows why the little bitty particles are electrical. Einstein said we cannot comprehend on theoretical grounds why matter appears as discrete electrical particles. These things are not known at the university, and that is not going to intimidate us. Why have I got these glasses on? Why doesn't somebody remind me that it's night?
Because you being south of the border, we don't want your roof.
I'm north of the border. All right, now what do we have to talk about? I want you to get these things straight that we went through yesterday. I want you to understand the geometry, that Einstein changed the geometry from 3D to 4D, and he changed and he left matter out of our physics. Matter left physics in 1905, and all that's left is energy. And the energy is the nature of the underlying existence showing through. If you see it spaced out, the undividedness, which is the nature of the reality showing through, makes it all fall together like a stretched rubber band. And if you mistake the infinite for the finite, the infinite shows here. And that winds it up to 500 nanomiles per pound. Don't you see how funny it is? This thing that we call inertia is energy. That's what energy is. We have different names for it. We call it energy, we call it mass, we call it inertia. It's all the same thing. It's the nature of the underlying existence showing through. That's all. And you can't change the amount of it. And we have conservation laws. Do you all understand conservation laws? Let me read to you some more. If I can find that one fast enough. That's, I think, 83. There we go. 83. Well, he's talking here about the conservation of energy, but I'll read a little bit over here. Therefore, conservation laws are very interesting. The question naturally arises as to what other conservation laws there are in physics. There are two other conservation laws which are analogous to the conservation of energy. Do you all understand the conservation of energy? The energy that goes into some operation is always equal to the energy that comes out. You never get any new energy from doing anything, and you never get rid of any energy by doing anything. Always the energy that goes in is the same in amount as the energy which comes out. It's just like pouring gold. If you have 2 quarts of gold, you can pour it into bracelets, you can pour it into rings, you can pour it into images of some god or goddess. Don't make no never mind. You never get rich by remelting it and pouring it again. You always have the same amount of gold. Well, the energy is like that. There's nothing you can do about it. There's no way to get any more. There's no way to get any less. And the problem is, what is it? It's the nature of the underlying existence showing through. Anyway, so there are 2 other conservation laws which are analogous to the conservation of energy. He's been talking about the conservation of energy. It doesn't come in little pieces so you can count the pieces. It can come in any amount. But when you get to the end of your operation and you add all the little pieces up, they come out to be the same as what you put in. So he says there are 2 other conservation laws that are like that. One is called the conservation of linear momentum. The other is called the conservation of angular momentum. We will find out more about these later. Now listen to this. In the last analysis, we do not understand the conservation laws deeply. We do not understand the conservation of energy. We do not understand that energy comes in little lumps, you see. It doesn't. You might think the photons come in little lumps, but you can have any size lump you like, you see. So it doesn't work out like that anyway. So now he's going to talk about some other things. And he says, in quantum mechanics, the concept... Hang on, let me go back a little. So we do not understand this energy as counting something at the moment, but just as a mathematical quantity, which is an abstract and rather peculiar circumstance. In quantum mechanics, it turns out that the conservation of energy is very closely related to another important property of the world. Things do not depend on the absolute time. We can set up an experiment at a given moment and try it out, and then do the same experiment at a later moment, and it will behave in exactly the same way. And don't make no never mind. When you do your experiment, it works just the same way. It's in the goddamn dependent of when you do it. If we assume that that is true, and add the principles of quantum mechanics, then we can deduce the conservation of energy. Isn't that neat? It is a rather subtle and interesting thing, and it is not easy to explain. The other conservation laws are also linked together. The conservation of momentum is associated in quantum mechanics with the proposition that it makes no difference where you do the experiment. The results will always be the same. As independence in space has to do with the conservation of momentum, independence of time has to do with the conservation of energy. And finally, if we turn our apparatus any old direction, this too makes no difference. And so the invariance of the world to angular orientation is related to the conservation of angular momentum. Now you see, in another place he says, these are amongst the most beautiful things in physics. Why, when you add quantum mechanics, you get these interesting things? I wish I had the other quote, but I don't have it with me. Now you do all understand these conservation laws. How many of you watched one of those stupid pendulums that swings and knocks over the pegs? You all have, haven't you? Put up your hands if you've watched them. I want to know that you watched them. What does the pendulum keep track of?
The tilt of the earth.
What keeps track of the spin of the earth? It doesn't give a damn about the spin of the earth. And the earth spinning around pushes the pegs in front of the pendulum, and it pays no attention to it and knocks the pegs over. I want to know what it does pay attention to and not what it ignores.
Pays attention.
However, you've got it the way they write it.
Okay.
They always write it that way. They don't know what else.
Well, I read it while I was there.
It pays no attention to the spin of the earth, so what does it pay attention to? Itself? No, you can't pay attention to yourself. It pays attention to something.
Conservation of energy.
What?
Conservation of energy.
All right, keep going. You're not quite right, but you're on the border.
It pays attention to inertia, doesn't it?
It's what?
To inertia. It keeps going the same direction because there's no force acting on it.
Yes, I know. Same direction with respect to what?
Well, the direction it was going.
With respect to what?
What's making it move?
What?
What's making it move? Because it
Well, they
doesn't
started
move.
at 9 in the morning. They started at 9 in the morning. They had that big heavy ball. And then up in the ceiling, they have a little thing which can't change the direction of the spin. No, not up there. The joint up there doesn't change, it's fixed so it can't change the direction of spin. And right under where it swings over, they have a little magnet. So when it's coming in here, it speeds it up quite a bit. But it doesn't change its direction. So that's how they keep it going. They can keep it going all day and all night if they want. But the planetarium building spins around underneath it and puts the pegs in front of it. And I want to know what the pendulum pays attention to.
Linear momentum.
Well, keep going. I asked for a fish and you give me a lake again. I know where the lake is. She's talking with her hand. Thinking with her hand. I'll have to tell you a story.
I guess the pendulum is swinging in relation to the center of gravity of the Earth. Right?
It doesn't give a damn about the center of gravity of the Earth. So now we're going to take it off the Earth so that it clean up the picture, okay? Instead of doing it that way, we're going to have a pistol that is loaded in count and it's radio controlled, and the barrel is rifled so that the bullet's going to spin out this way. So it's out there between the stars, and we tell it to shoot. So the bullet spins out this way. What does the gun do? Spins back this way. Is the spin of the bullet equal to the spin of the gun? Look backwards. Yes, they are. Is the linear momentum of the bullet equal to the linear momentum of the gun? Yes. The bullet is lighter and it goes faster. The gun is heavier and it goes slower. But momentum is the mass multiplied by the speed. So in one case the speed is big and the mass is small. In the other case the mass is big and the speed is small. And there's a moral to this. Never shoot a pistol that weighs less than the bullet. Now you know in Star Trek, Kirk sets his phaser on stun and shoots somebody over a counter. Kirk would also go over a counter, you see. But Star Trek pays no attention to the rules of the real world. And when Star Trek was new, I lived in a house with 3 teenagers, and I used to like to watch Star Trek with them. They used to say, either shut up or get out.
That's good.
All right, so now for a while you can think, that the gun keeps track of the momentum of the bullet, because the momentum of the gun is just equal to the momentum of the bullet with an opposite sign. If that one's going this way, this is going this way. If that one's spinning that way, this is spinning this way. All right. But we're going to let the bullet fall into a supernova star just before it blows up. And now the momentum of the bullet is scattered all over the galaxy. What does the gun keep track of now? Gotcha, huh? She's snickering. The other half of the gun's momentum is packaged in the rest of the universe. You can put it anywhere you like. Momentum is always half of something. And when that thing blew up, it did not change the momentum of the universe. One half went off that way, and the other half went off this way, and nothing has happened to the universe. But the other half of this momentum is still in the rest of the universe. And this stupid gun has to keep track of the whole damn thing. Now, I tell kids, you know, when they're watching that pendulum swing, if you can watch that pendulum swing and not get goosebumps, you are asleep. That stupid pendulum has to keep track of all the rest of the universe, because the other half of its swing is there. If it weren't for that, our inertial guidance systems would never get us anywhere. We would never have been to the moon. Now, you know that this is true because we've been to the moon. There you have it. You know that this is true because we've been to the moon. All right, what else do we have to talk about? I'm trying to get these things solid away in your guts. I don't want any of you to lose track of what's written here on this board. If you see things in space and time, there's a limit to what you can find out about it. If you mistake a rope for a snake, there's a limit to what you can find out about the snake. That's this one. But if you see things in space and time, they're going to be wound up against gravity because the undivided shows through. We're wound up against electricity because the infinite shows through. And the geometry is a 4D geometry, so that the separation between us and what we see is zero. But now, have you got it all sorted away, the stuff we said yesterday? You see, we have mistaken the changes for the changing, the infinite for the finite, and the undivided for the divided. And you cannot do it in any other way except by a mistake. You can't change the changes into the changing. Now, the curious thing about this whole model is that it gives the universe which we see. It gives the physics which we see. The physics of gravity, electricity, and inertia. Not some fake physics, like the Big Bang people have us think. They've got all kinds of fake physics for us to think about. Dark matter that responds only to gravity, X particles that make matter into antimatter, anti-X particles that make antimatter into matter, monopoles. They got a whole bunch of stuff for us to think about, which doesn't, so far as we know, don't exist. This gives you the physics of the universe which we see. If you've got it solid away, I'll start on something else. But if you've got any more questions, raise them.
I'm still thinking about the separation. You said that the separation between us and what we see is zero?
Yeah.
Does it mean that what we see is us?
No, it doesn't exactly mean that. But in a sense, it does mean that. I said that what exists behind what we see is undivided. If it's undivided, there's only one of us. Okay? There's only one of us. Now you see, it looks to us as though there are lots of us.
I can't listen to them.
It looks to us as though there are lots of us. And there's lots of soft evidence for the plurality of the perceiver. There is no hard evidence in our physics for the plurality of the perceiver. One of the fathers, if you like, of quantum mechanics, he hated being father of quantum mechanics, is Erwin Schrödinger. He said consciousness is never experienced in the plural. Now you see, when we dream, we see a whole lot of people in the dream. And so long as we're dreaming, we got a plurality of observers in our dream. When you wake up, all of a sudden you see it was a mistake. You put all those nasty words into their mouths. Okay? Now, the physics says that it might be so when we're awake. Now let me give you an example. Suppose you dream that you're a little girl in the library and you found this great big book and it's got a problem in it which you cannot solve. And after thinking about it for quite a while, you take the book to the librarian's desk and lay the book in front of the librarian and explain to her that there is this problem that has arisen in your mind. And she scratches her head and she can't figure it out either. So she goes back into the stacks to see if she can find it out in the back of the library. After some time, she comes forward again to her counter, and you stand there with bated breath to get the information from the librarian. Now, when you wake up, then you can see that you were the little girl in the library, and you wrote the big book. And you raised the problem in the big book, and you were the librarian. And you wrote all the books in the stacks. And you stood there and waited with bated breath to get the information from yourself. Now, if you can do it asleep, you can probably do it awake. Most of us are more successful awake. Yeah.
Do teachers really teach themselves then, given that model?
Teaching really is somebody pointing out something which is already obvious to you somewhere along the line. I'm just here to suggest things. You guys have to figure out whether it's obvious or not. I don't have to do that. All I can do is to say, look at this side, maybe it's like that. That's all that anybody can do for anybody else. Always, the student has to do all the work. Always. In one of those old Upanishads, there's this very interesting statement. Talkers, we have aplenty. Listeners are scarce. But really, unless somebody presents it to you so that you can see that it's obvious, he hasn't done his job. And your job is to see that it's obvious, and that's because of something that happens in you, not something that happens in the teacher. All he can do is to toss around several ways of looking at it, and you pick out the one that makes sense for you. But you have to do all the work.
You also use the term boo-boo.
I like the term boo-boo.
Define it in the way that you were explaining it.
I just mean that we mistook one thing for another, like mistaking a rope for a snake. I give you that illustration all the time. That's all I mean. I don't mean like spilling the milk. I'm that kind of a boo-boo. Or pig in your Huggies.
That's later on in life.
Could you please tell something more about the consciousness?
Sentiency is in this thing from the word go. Remember I said we have these senses of perception? That consciousness is connected with all those things. And we know we're down here. But you see, the lead also knows where down is. Matter is also sentient. Every electrical particle reads every other electrical particle. And everything with gravity reads gravity. And I asked her today if she'd buy a watermelon. She's got a little scale. It's about this, the thing goes around about that far, you see. So we can put a watermelon up here and then take a picture of it. Now in one case, and then we're going to turn it over and reset the 0. Then we're going to put the watermelon on top. And it's going to read the same thing it read before. Then we're going to have a picture where we show them both with the scales right side up. Now in one case, it's how much the watermelon weighs the gravitational field of the Earth. In the other, it's how much the Earth weighs the gravitational field of the watermelon. Is there any question about that?
I don't understand anything.
Well, at least if you don't understand anything, you're out of trouble.
I've done like...
Does your body have a gravitational field?
I think so.
It does. Otherwise, you could not tell that the Earth had a gravitational field. It's only your gravitational field that reads another gravitational field. Only gravitational fields read gravitational fields. Only electrical particles read electrical particles. Nothing else but electricity reads electricity. And nothing else but gravity reads gravity. Got it? So you have a gravitational field, and the question is, how much do you weigh in the gravitational field of the Earth? The other question is, how much does the Earth weigh in your gravitational field? They're the same number. They're the same number. And I always wanted a great big scale like this, you see, so I can stand on here and how much I weigh in the gravitational field of the Earth, and then turn it over and how much the Earth weighs in my gravitational field. That's how I wanted it, but I've never been able to find a scale with a big enough thing so that the camera will show it. But you see, with her nice scale, this side, and a watermelon, we can do it. I can't stand at her scale, squash it.
I'm not really sure whether the answer fits to my question.
Let ask your question again, please.
Because I wondered about what you said about consciousness.
Consciousness is just an extension of sentiency.
And
Matter.
What does it mean, essentiency? I don't know.
Awareness.
Ah, okay.
Awareness.
Right.
This chair is aware of where the Earth is. It knows exactly where the Earth is. I know you think that I'm smart and I know where the Earth is and the chair might not know. No, the chair knows where it is. Want me to show you? The chair knows where the Earth is. Matter knows about matter. It's conscious of matter, if you like to use the word conscious. I don't mind if you use the word conscious. What I don't like to do is to use conscious for us and sentiency for something else. That I don't like. There's no line between these things. If this is a boo-boo, there's always a boo-booer. You can't have a boo-boo, this kind of a mistake, without a conscious being to see it. It's a sentiency problem. Now, we were taught, when we were kids, that matter was inert and it doesn't see anything. That's bull, okay? That's cattle feces. There's no such animal in this world. There's something that's so stupid as that. Matter knows where matter is. It's better than it is in your dream. The waking state's a lot better than your dream. But it very probably works the same way. Now, I, years ago, saw what purported to be a documentary on near-death experiences. This was on my All Shades of Grey TV. And I listened to what they said. Never mind when they put the camera up in the corner. Never mind all that stuff. And it looks to me as though when you look out in this world, on that side is the world and the other side is you. And when you're passing away, it looks as though this thing backs off like this, and you see that this body is part of the perceived. Part of the perceived. That's what you see. And it's got a broken leg and they're working on it. That's what you see. And it's an it and not you. It has a broken leg. They're working on it. And you don't want to get back in it. That's the way they talk. Now you see, if this arm is cut off at the elbow, you will all see that it's not part of me. I would also see that it's not part of me. If it's not part of me cut off, it's not part of me cut on. This is just a genetic programming that makes us think that we're made out of meat. You know, I didn't read the Oz books till I was grown up. And I was very much amused. There's a straw man. He has to be careful about matches. He can't play with matches. It's inflammable. And there's somebody that's made out of tin or iron or something. He's afraid of rain because he rusts, you see. And Dorothy's afraid of knives because she's made of meat. Well, anyway, I didn't read it till I was grown up. But I think the impact on me was much bigger than it is on the kids. Well, you're not made of meat, okay? The body is made of meat, and they're going to put it in an incinerator and burn it all up. And you're not going to get in there. Now, my kid's mom tells me that on that last day when they put this body in a box, the mouth will still work. What?
It's got a longer life.
All right, now I asked you, what happened to us that didn't happen to the chimps? Are we ready for that? Are we still?
Yeah.
I don't want you to skip this until you're through with it. I want you to understand this thing perfectly clearly. As I said, if you can't handle these three statements, you've already thrown in your sponge. If you can't handle these three statements, you've already thrown in your sponge. But they're all easy. One at a time, they're perfectly easy. It's easy to see that all this stuff that we see as matter is just potential energy. It's perfectly easy to see. If you go down to a neutron star, 1/10 of it goes away. Go down to a small event horizon of a small black hole, 1/3 of it's gone. Go all the way down and it's all gone. It all goes to energy. But it all is energy already. It's just potential energy going to kinetic energy, that is all. So it's all energy and not anything else. And the energy is the nature of the underlying existence showing through. The changes shows through in us is our peace and search for peace and security, shows through in matter as inertia. The infinite shows through in us as our yearning for freedom. The infinite shows through in matter as the electrical charge of the itsy-bitsy particles. And the undivided shows through in matter as gravity, and it shows through in us as love. They all show through. Nobody runs after anything else. Did you ever see anybody running after anything else? They all run after peace, security, freedom, and love. But you see, the difficulty is that in this world, they're contradictory. So long as you see it in space and time, they fight with each other. Gravity wants everything falling together. Electricity wants everything flown apart. And inertia says, knock it off. And it's the same thing with us. We fall in love, then we get married, then our freedom is gone, and we want out. We did this yesterday. Then we're lonely, and we get back in. All the time we say, leave me alone. We want to be totally in love, totally free, and totally alone. And in this world of space and time, these are three different things looking from different directions, and they're self-contradictory. They're mutually contradictory. In the reality, that which is infinite is changeless, is undivided. But where we see it, there are three, because we look out these two windows. We got a time window, and on our side everything is changing. On the other side it must be changeless. That's what the other side means. And we got a space window, and on our side things are divided and finite. On the other side they must be infinite and undivided. But the reason we see these things as three is because we're looking through inside of space and time. And space and time is already three. It's already time against two directions in space, the in direction and the out direction. It's already three. That's why we see it as three. There aren't only three. There aren't three. The changes to the infinite and the undivided isn't three. Is that clearly or not clearly?
It's just, I think I should shut my mouth. Did I had the impossible, but it's like this undivided, all the state, like everything is, yes, what you said yesterday is like the universe is made out of frustrations, all those contradictory tendency.
If you see it in space and time, it's made out of frustration, and you must have noticed.
But it's possible, yes. But it's also possible, and sometimes once people have a glimpse of that all the
Yes,
things.
you can get a glimpse, but let me tell you how we do it in the art world. Suppose two people are in a concentration camp in Germany in World War II, okay? And they escape, and they get across into Switzerland, and then they get back to the United States. That's where the story ends. Do you know why? Because the next thing they did is get married and their freedom was gone. The story ends there. The stories end when they fall in love and get married and they live happily. They don't live happily ever after. They live happily for a week.
This is all in the same level of existence, in the same perception. But what I'm saying, it's possible sometimes to have the experience of what's not in that story.
Of course. What you are is what is beyond space and time. That's what you are.
But sometimes we have a bit of a sense of what...
That's right, because the nature of the reality always shows through. Now, the abbot of the monastery, he used to say, you see, in India, lots of people say, everything that happens to you because of what happened to what you did in the past. He says, bullshit. Well, he doesn't use that language, that's my language. But he says, always the nature of the reality shows through. You cannot blame everything that happens to you on something that you did in the past. You can't do it that way. There's always this thing beckoning you to go towards the reality. There's always this thing calling you. The universe is pulled from the front by the changes, the infinite, the undivided. It's not pushed from the back like Newton thought. Newton thought it was a clock pushed from the back. No, it's not pushed from the back. We're running toward the changes. We're running toward the infinite. We're running toward the undivided, not something else.
We're being pulled?
Pulled, yeah.
When you say that gravity reads gravity, electricity reads electricity,
Yes.
we're conscious. Are we seeing consciousness?
I try to avoid the word consciousness
Well,
because there's so many spooky notions
yeah.
tied up with it. For the
Perception.
same reason that I avoid the G word.
Hmm.
You see,
Do you understand?
Well,
Well, if you get through with the spookiness, do you understand what I'm asking, or do you?
yes, I don't mind if you use the word consciousness, but you see, the word consciousness is really tied up with duality.
Mhm.
One is conscious of the other.
Mhm.
And as soon as you get beyond the two-ness, the word consciousness falls through.
Mhm.
And for that reason, I don't like it. Now, in India, they say the two ways of referring to this ultimate reality. It changes infinite and undivided, like I do. I get it out of the physics. They don't do it this way, but they got the same kind of words. We have in the hymn books, "Oh, thou who changest not, abide with me." We've got it all in the hymn books. You must have noticed. Anyway, in India, they have this other way of describing it as being consciousness bliss. Now that, they say, is like pointing to the cottonwoods. Now, I used to live in Sacramento for 9 years, and about a mile from the American River. Now, all along the American River, there are cottonwood trees. They stick way up above the river. They stick way up above, so you can see them from miles away. And if somebody asks you where the river is, you point to the cottonwoods. You see the cottonwoods? That's the river. It's not the river, it's the cottonwoods. But if you get to the cottonwoods, you'll be on the way to the river. And so they say that that's an approximate thing. Go towards being, don't go towards non-being. Don't go towards consciousness, don't go towards unconsciousness. Go towards bliss, don't go towards sorrow. So they say that being consciousness bliss is an approximate description, showing you which way you go. But you can't put your finger on it. There's never any way to say it rightly. You can say it approximately, or you can say it negatively. You can never say it rightly. Now, Sri Ramakrishna used to say that just as food coming out of the mouth is polluted, anything you can say about the reality gets polluted by coming out of your mouth. That's called having a dirty mouth. Yes.
Would you, just kind of wondering, would you agree that of all living organisms on the earth, we're, of course, the most intelligent, and probably way more intelligent than we really have to be to survive on the earth? Other organisms you find without this intelligence that we have. We have the ability to perceive matter, which in such a way that no other organism could perceive it. And really, we're going beyond what the natural state of this earth.
This is called human egotism. Go on.
Probably, yes. But anyway, because of our intellectual abilities, we're going way beyond what natural state would. If we had a less of an intelligence, we could kind of stay in harmony with that natural state. Our abilities take us way beyond that, but not by mistake, I would think. And what I would think is that because of our curiosity to understand what the universe is made of our destiny really is to explore the universe and to actually try to probe the deepest part of you.
One of the things that we have to talk about, I don't know whether we're going to get to it tonight or not, but one of the things that we have to talk about is what happened to us that didn't happen to the chimpanzees. Because we have a suspicion that we think about problems in a way that the chimpanzees don't. We certainly have this suspicion. Anyway, there's another thing I was going to ask you about. I forgot what it is. Shucks. Anyway, we have to talk about the borders of the universe also. I'm not ready yet to talk about what happened to us that didn't happen to the chimps, but we're going to get to that. We have to get to that. How come we're so curious? And they always say the chimps never come in here because they're never as curious as you guys are. And if you guys weren't curious, none of you would have come here to do some ice cream farm.
May I ask some more questions?
Yes, you may.
If we are what is beyond space and time, why do we need space and time?
You don't need space and time. The question is, you see, let me go through this again. There are two kinds of things which I call causation. Ordinary causation, like if I drop my keys or something, you see, they have gravitational energy. I keep in the bag because they won't go through my pocket, you see. I have both in my pockets. Anyway, so they have gravitational energy up here. If I let go, they have kinetic energy. This one becomes that one like that, okay? What am I telling you about? But that's what we call ordinary causation or transformational causation. The gravitational energy is transformed to kinetic energy as this thing falls. Is that clear? This one goes away and that one gets bigger. That's called transformational causation. The amount of energy never changes, but it's the conservation laws here. But the form of the energy changes in all these operations that we do. Like talking. I make sound energy, it deposits on the wall, enters up as heat energy. Okay? So this is called transformational causation. And you never get anything out that you didn't put in. But there's something else which I call causation, like mistaking a rope for a snake. I call that apparitional causation. Now transformational causation, like making milk into buttermilk, is a happening in time. There's a date on it, when it happened. You had milk, then you put in some culture, kept it a little bit warm, 86 degrees, and by gum in the morning you had buttermilk. Okay? There's a happening in time, and there's a shelf life on your buttermilk. But mistaking a rope for a snake is not a happening in time, and the question about it is very different. The question is not how did it happen, or when did it happen, or any of that. The question is why do you go on with it? It's not as though yesterday you mistook the rope for a snake, and now there's a snake in the living room, and you're staying in the kitchen with the door closed. It's not like that. It's something you're doing now, and the question is only, why do you do it? So that's what we have to talk about. What happened to us that didn't happen to the chimpanzees? Because we don't have to go on with this. So far as we know, the chimpanzees have to go on with it. So far as we know, the dogs have to go on with it. And so far as we know, we don't. But it takes some hard doing to don't. It's not all that easy. But it takes some hard doing and you can don't. Anyway, we need to talk about the borders of the observable universe. And we need to talk about the Big Bang. And this, okay?